Welcome. I'm MB, and I want to take you on a journey not through the vastness of interstellar space, but into the heart of a substance so familiar we often overlook its profound cosmic significance. It's a molecule that surrounds us, fills us, and in many ways defines us. We drink it, bathe in it, cook with it, and yet how often do we pause to consider its truly alien nature? This substance, common as it may be on our world, is an anomaly in the grand theatre of chemistry. A maverick that bends the very laws of physics to its will, enabling the improbable miracle of life on this pale blue dot. Prepare to meet a liquid that breaks the rules. It flows uphill, floats when frozen, climbs trees, cools deserts, and cooks your food. It's a chameleon, a shapeshifter, a fundamental force hiding in plain sight. This isn't just any liquid, it's the architect of our world, the sculptor of landscapes, and the silent partner in every breath you take. It breaks the rules of chemistry, and that's the only reason you're alive. Without its eccentricities, its defiance of molecular norms, the story of life on Earth simply could not have been written. So, come with me. Let's explore the astonishing properties of this everyday marvel, this cosmic rebel we call water. We'll delve into its secrets, uncover its paradoxes, and witness how its refusal to conform to expectations has paved the way for complexity, for consciousness, for you and for me. Our understanding of the universe itself is deepened when we appreciate the extraordinary nature of this seemingly ordinary compound. The story of water is, in essence, the story of us. Consider the act of freezing. For almost every substance in the known universe, the transition from liquid to solid is a journey into greater density. Molecules huddle closer, packing themselves into rigid, compact structures. As they cool, they shrink. This is the expected behavior, the norm dictated by the fundamental laws of thermodynamics. If you were to freeze, say, liquid iron or molten rock, the solid form would promptly sink beneath its liquid counterpart. This is how the universe usually works, a predictable dance of atoms and energy. But water scoffs at this convention. As it approaches its freezing point, it begins to do something utterly remarkable, something that defies the common logic of chemistry. Instead of becoming denser, it expands. Its molecules, two hydrogen atoms bonded to an oxygen atom, arrange themselves into a crystalline lattice structure that is surprisingly open, less compact than its liquid state. This molecular ballet results in solid water and ice being less dense than liquid water. It's a subtle rebellion, but one with planet-altering consequences. Imagine a world where water behaved normally. As lakes and oceans cooled in winter, the ice forming on the surface would sink. Layer upon layer of ice would descend, eventually filling the entire body of water from the bottom up. Imagine a skyscraper, hundreds of feet tall. Now, imagine trying to transport water from its foundation to its very pinnacle without any mechanical pumps, without any discernible external force. It sounds like an engineering impossibility, a violation of the fundamental force of gravity that anchors us to our world. Yet this very feat occurs every second in countless locations across our planet, performed silently and efficiently by the plant kingdom. All thanks to another of water's extraordinary talents. This is the magic of capillary action. Water's astonishing ability to climb upwards against the relentless pull of gravity through narrow spaces. It's a consequence of two powerful forces at the molecular level: cohesion and adhesion. Cohesion is the tendency of water molecules to stick to each other, a result of the hydrogen bonds that link them like a microscopic chain. Adhesion is water's inclination to stick to other substances, particularly those with charged surfaces, like the cellulose that forms the walls of a plant's xylem vessels. In the slender, straw-like tubes within a tree's trunk and branches, these forces combine in a beautiful synergy. Adhesion pulls the water molecules upwards along the sides of the vessels, while cohesion ensures that the column of water molecules behind them is dragged along for the ride. It's like a microscopic bucket brigade, each molecule pulling its neighbor, inching skyward. This process, transpiration, is further powered by the evaporation of water from the leaves, creating a gentle, persistent tension that draws water up from the roots. Consider the giant sequoias of California, or the towering eucalyptus trees of Australia, some reaching heights of over 300 feet. Water journeys from deep within the earth to their uppermost leaves, nourishing every part of these colossal organisms. Mangrove trees, standing defiantly in saline coastal waters, perform a similar feat, drawing fresh water against both gravity and osmotic pressure. Even the humble vine, clinging to a cliff face, relies on this silent molecular ascent to sustain its lofty perch. Our planet is a dynamic place, subject to the fierce, unwavering energy of a nearby star, our Sun. By day, its radiation bathes the Earth, and by night, that energy radiates back into the coldness of space. This constant cycle of heating and cooling could lead to extreme temperature swings, making life a precarious venture. Yet, many regions of our world experience a relative thermal stability, a moderation of these extremes. A key player in this global climate regulation is, once again, water, acting as a colossal thermal battery. Water possesses an unusually high specific heat capacity. This means it takes a lot of energy to raise the temperature of water by even a small amount, and conversely, water releases a significant amount of heat when it cools. Compared to land or air, water is a thermal heavyweight. It resists rapid temperature changes. It absorbs heat slowly and releases it slowly, acting as a massive buffer against thermal volatility. Think of it as nature's own energy storage system, diligently working to smooth out the thermal chaos. Oceans, covering over 70% of our planet's surface, are the primary manifestation of this thermal battery. During the day and throughout the summer months, they absorb vast quantities of solar radiation. The sun's anger, its intense energy, is soaked up by the deep blue, stored within the restless motion of water molecules. This prevents the land from overheating to unbearable temperatures. The sheer volume of water in the oceans means they can store an immense thermal charge without their own temperature skyrocketing. Then, as night falls or winter approaches, the stored heat is gradually released back into the atmosphere. At the boundary where water meets air, something extraordinary happens. The surface of the water behaves not like a loose collection of individual molecules, but more like a stretched elastic membrane, a delicate, invisible skin. This phenomenon, known as surface tension, is another consequence of water's powerful cohesive forces, the hydrogen bonds that make water molecules cling so tightly to one another. At the surface, with no water molecules above them, the surface molecules are pulled inwards and sideways by their neighbors, creating this tautness. This skin is remarkably strong for its infinitesimal thickness. It's strong enough to support objects far denser than water itself, provided they don't break the surface. You've seen it in action. A carefully placed needle can float on water, defying its metallic density. More impressively, entire ecosystems have evolved to exploit this unique property. Tiny insects like water striders glide effortlessly across ponds and streams, their specialized legs distributing their weight so as not to puncture this molecular trampoline. For these creatures, the water's surface is not a barrier, but a habitat, a hunting ground, a place to live and reproduce. Spiders, like the fishing spider, can detect the vibrations of struggling insects trapped on the surface film, using it like a vast liquid web. Some insects even lay their eggs on the underside of the surface layer, trusting its integrity to protect their developing offspring. It's a miniature world teeming with life, all made possible by the collective grip of water molecules. But the utility of surface tension extends beyond these macroscopic dramas. At the microscopic level, it influences countless processes. The formation of dewdrops on a spider's web, clinging precariously yet perfectly spherical, is a testament to surface tension minimizing surface area. Every day, an immense and largely invisible transformation takes place across our planet. Billions upon billions of tons of water silently depart from the surfaces of oceans, lakes, rivers, and even from the leaves of plants, ascending into the atmosphere. This process, evaporation, is the conversion of liquid water into its gaseous state, water vapor. It's a quiet exodus driven by the energy of the sun, but its scale is monumental, its impact global. Water molecules in a liquid state are in constant motion. Some, near the surface, gain enough kinetic energy from solar heating or ambient warmth to break free from the cohesive forces holding them to their neighbors. They escape into the air as individual, invisible molecules of H2O. This isn't a forceful eruption, but a gentle, persistent diffusion. The warmer the water and the drier the air, the more rapidly this molecular escape occurs, carrying vast quantities of water into the sky. Consider the sheer scale. The world's oceans alone lose an estimated 1 meter of their depth to evaporation each year. That's a colossal volume of water lifted invisibly into the atmosphere, forming a vast, flowing river of moisture that encircles the globe. This atmospheric river, unseen by the naked eye, is a critical component of the Earth's hydrological cycle. It transports water over immense distances, from equatorial oceans to arid continents, from warm seas to cold mountain ranges. This vapor is not just water, it's also stored energy. The process of evaporation requires energy, the latent heat of vaporization. This energy, absorbed from the sun or the water body itself, is carried aloft with the water vapor. What goes up, as they say, must come down. The vast quantities of water vapor that ascend into the atmosphere through evaporation do not remain there indefinitely. As this invisible atmospheric river meanders across the globe, it encounters changing conditions, cooler temperatures at higher altitudes, or when air masses are forced upwards by mountains or weather fronts. This cooling is the trigger for the next crucial phase of the water cycle, condensation. Condensation is the magical transformation of water vapor, that invisible gas, back into liquid water. As air cools, its capacity to hold water vapor decreases. The energetic, free-roaming water molecules slow down, and when they collide with tiny airborne particles, dust, pollen, salt from ocean spray, even microscopic pollutants, they begin to coalesce. These particles act as condensation nuclei, providing a surface upon which the water molecules can gather, forming infinitesimally small droplets. As more and more water molecules join these nascent droplets, they grow. Billions upon billions of these tiny droplets, suspended in the air, become visible to us as clouds. Clouds are not just pretty formations in the sky. They are colossal reservoirs of liquid water, or sometimes ice crystals, held aloft by air currents. They are the visible manifestation of water's return journey, a crucial stage before its descent back to the Earth's surface. When these cloud droplets grow large enough, heavy enough that the updrafts can no longer support them, gravity takes over. They fall to Earth as precipitation, rain, snow, sleet, or hail, depending on atmospheric conditions. This is the lifeblood of continents, the replenishment of rivers and lakes, the sustenance for forests and fields. Without condensation and the subsequent precipitation, the water evaporated from the oceans would never return to irrigate the land, and terrestrial life as we know it would wither and vanish. When we think of food, we often picture the fruits, vegetables, and grains that grace our tables. But what is the fundamental process that creates this nourishment? Plants, the primary producers in most ecosystems, don't make food from nothing. They are, in essence, culinary alchemists, transforming simple inorganic ingredients into the complex organic molecules that fuel life. And at the heart of this remarkable culinary engine is water. The process, of course, is photosynthesis, a word that literally means making things with light. Plants capture energy from sunlight and use it to convert carbon dioxide from the air and water from the soil into sugars, primarily glucose. This glucose is the basic fuel, the stored energy that powers the plant's growth and eventually nourishes any creature that consumes the plant. Water plays multiple indispensable roles in this foundational life process. Firstly, water acts as the transport medium. It's absorbed by the roots and, through the capillary action we've discussed, travels up to the leaves, the primary sites of photosynthesis. This water carries with it dissolved minerals and nutrients from the soil, essential building blocks that the plant incorporates into its structure. Without this aqueous delivery system, the raw materials for life's construction would never reach the cellular factories where food is made. Secondly, and most critically, water is a direct reactant in the photosynthetic equation. During the light-dependent reactions of photosynthesis, water molecules are split apart, a process called photolysis. This splitting releases electrons which are energized by sunlight and used to create energy-carrying molecules. It also releases protons, contributing to an energy gradient. Imagine for a moment a parallel Earth, a world where water behaved like any other typical molecule. A world where ice sank, where capillary action was feeble, where water heated and cooled rapidly, and where its surface tension was negligible. What would such a planet look like? The answer is stark and sobering. It would likely be a sterile, cold, and profoundly dry place, utterly inhospitable to life as we know it. If ice sank, our oceans and lakes would freeze solid from the bottom up, extinguishing aquatic life and locking away vast quantities of water in a permanent frozen state. Without robust capillary action, trees could not grow tall, forests would not exist, and the terrestrial landscape would be barren, unable to draw moisture effectively from the soil. The very greening of our continents, a hallmark of Earth's vitality, would be an impossibility. If water lacked its high specific heat capacity, our planet would experience wild temperature swings. Deserts would scorch by day and freeze by night. Coastal areas would offer no thermal refuge. The delicate biochemical reactions that underpin life, which require a relatively stable temperature range, would be constantly disrupted, making the evolution of complex organisms extraordinarily difficult, if not impossible. The climate would be a chaotic, unpredictable torment, and if water's surface tension were weak, the intricate dance of life on the water's surface film would cease. Raindrops might not form as readily. The delicate mechanisms within our lungs and similar structures in other organisms that depend on managing surface tension would fail. The very fabric of countless micro-habitats and physiological processes would unravel. The subtle yet crucial interactions at the air-water interface would be lost. Beyond its thermal and physical peculiarities, water possesses another remarkable characteristic that is fundamental to life and to the shaping of our planet: its exceptional ability as a solvent. Often dubbed the universal solvent, water can dissolve more substances than any other known liquid. This isn't an arbitrary trait, it stems directly from the polarity of its molecules, those little V-shaped structures of oxygen and hydrogen. The oxygen atom in a water molecule has a slight negative charge, while the hydrogen atoms carry slight positive charges. This makes water a polar molecule, like a tiny magnet with a positive and negative end. When water encounters other polar substances or ionic compounds, like salts, its charged ends can exert an attractive force, prying apart the individual ions or molecules of the solute and surrounding them. This process of dissolution is essential for countless natural phenomena. Think of the oceans. They are not just vast bodies of H2O, they are a complex soup of dissolved salts, minerals and gases. Rivers tirelessly erode rocks and soil, carrying dissolved minerals to the sea, making the ocean salty and providing the raw chemical ingredients that marine organisms use to build shells, skeletons and cells. Without water's solvent power, these vital nutrients would remain locked within the Earth's crust, inaccessible to life. Within our own bodies, and indeed within every living cell, water acts as the medium for life's chemistry. Nutrients from our food are dissolved in water and transported via our bloodstream to every cell. Waste products are dissolved and carried away. The intricate biochemical reactions that define metabolism, the breaking down of food, the building of proteins, the replication of DNA, all occur in an aqueous solution. Water is the stage upon which the drama of cellular life unfolds. We have journeyed through the many wonders of water, this seemingly simple molecule of 2 hydrogen atoms and 1 oxygen. We've seen it defy expectations, bending the rules of chemistry and physics to create a world capable of nurturing life. From the ice that floats, shielding aquatic realms, to the capillary action that greens our continents, water reveals itself not as a passive substance, but as an active participant in the cosmic story, a dynamic force that sculpts planets and cradles biology. Think about it.